Hello, everyone. All right. I think we're good to go here. All right. So today we are continuing with USD Scale. USD Scale is the module for creating skeletal rigs and skeletal animation. And so last week we were looking at just trying to get a basic understanding of how uh, bones and meshes are bound together and how bones are laid out and all that. Um, and we found this handy asset here for just a basic arm. It's got a shoulder, elbow, and wrist, and we were looking at that. I think I've got a fairly good understanding of how it works. So I thought next up we could try to write the code for this, see if there's any if we get tripped up on any API, finding the right APIs for doing this. Um, so that's what we're going to be working on today. If you're here, let me know in the chat. Say hello. And some things that I found since last time is are there are we learned that the joints are defined simply as an array, as a property, for as an array on a property called joints on the skeleton prim. So instead of like some DCCs where you would see the bone hierarchy in your outliner, you don't see it here. All you see is a skeleton and an animation, and it's all vectorized here in this array. So, but you can there at least in USD View and also in USD Composer, you can see a joint representation in your viewport to understand what's going on here. The way that you get that is with display purpose. You have to have guide on. I think that was it. Let's take a quick look. It was that. Um, I think if it's not showing up, have a look at those display purposes. I was pretty sure I turned on guide to get that to start showing up. I don't think there was anything else here. And so let's do, just for something a little bit more interesting, let's go back to the character that Pixar provided here in the USD scale example. We do the walk. And there it is. Will you go away if I uncheck you? No. There we go. So that did go away. Odd. But yeah, we can hide all of these. What's in right? Maybe we need that one. And then if I did turn on this display guide, now we get the bones. And we can just watch the bones do their thing. It's a nice walk cycle. All right. So I think that's going to be handy for developing and visually verifying what we're doing. So let's go ahead and stop that and go back to our arm. And here we go. Good. Also, I think this still has the translation that I put on the elbow, which we can get rid of soon. Um, and then I've started this script out. Um, we're going to be writing a new stage above this scripts directory, and we gotta do a bunch of setups and code here. So first thing is just good practice to set up that world transform. You can call that transform whatever you want, but you do want to set that transform as the default prim. That way, if you ever reference this, you have a default target for your reference or payload. Um, so we got that. And then now we can go ahead and create a mesh. I don't think I even need that, but that's good practice. I've started using the types USD Python package, and I think it has pretty good type hinting here. So we're going to do mesh, define, pass the stage, and then the path. I'm just going to hard code the path here. Arm mesh. I guess we can be a little bit more organized. What do we think? Well, we should probably mirror. Like build it like this is built. So we need the skeletal root, and then they put the mesh, the skeleton, and the arm under the skeletal root, which makes sense. So that way, I think they'll translate together when you move that model prim. Okay, so we'll do scale root is probably going to be under USD scale. That's not the one that I want. Probably root. That makes sense. Stage, and there's a couple here. I'll give it a prim. Oh, I'm sorry, because I got to do define. There we go. And the path will be world arm, and then world arm mesh, and then lastly skeleton. Define. We can abbreviate these. Let's try that out. I should be able to run this here. So it wants a prim. Duh. So default prim wants a prim. Yep. All right. Let's do Not sure why I didn't like that one, but we can keep doing it here. There we go. So that should have written out our... Do I need to refresh? It didn't error out. Just as a sanity check. Did I need to... Shouldn't need to give it a path for that. There we go. I see. So it actually put it one folder up because I'm running my current working directory as my the root of my project. Okay, well that's fine with me. Okay, so we have Xform, scale root, mesh, skeleton. Everything's looking good so far. So let's continue. I'm gonna just spread this out a little bit. And here we need to set up our points attribute. And this is going to want a 0.3f. So a vector 3f should work just fine here. So we need to import graphics foundation, and we need to create this this array. Points is equal to vec 3 gf vec 3f array, and we can do an array like that, and I'm going to copy it from here. So that I just opened up the original asset, the USDA file, and I'm going to copy these points. And just to help make sense of this, it looks like 0 in the Z. What is going on with my indentation here? And then 2, and then 4. So all I'm doing here is just organizing them along the Z-axis so that I know. The first row is my vertices for the shoulder. Then the second row is the elbow, and the last is the hand. I kind of want to smash this over here. Okay, that should hopefully keep me sane for when I'm binding these. And keep in mind, I am hard coding the mesh and kind of manually thinking about how I'm going to be binding these in a real world scenario. You're probably translating a skeleton from one format to another. So it's more about how do I translate the way that this data is represented in, say, Maya to USD. So it's more algorithmic than what I'm doing here. But you may have one-off scripts where you may want to just code something rather than building it in a DCC. So okay, so we have our points. It doesn't look like we have these face vertex indices. I'm gonna hate myself for this because these face vertex indices are built off of this. So as much as I wanted to keep this ordered in a way that made sense to me, I'm gonna have to maintain the order that was here. Sad. And I'll explain in a moment why. So this is basically explaining the connectivity of the vertices in order to create a face. And so say the first face has 4 vertices, 2, 3, 1, and 0. 2, 3, 1, and 0. Um, and that makes the first face. And that's talking about the hand vertices, right? So while I could try to also translate this into my preferred order, I'm not going to bother. I'm probably going to make a mistake along the way. So we'll maintain the order. It's fine. So we're going to create these points using that array. And then we're going to do another GF vec. But this is just going to be what is this? It's just an int array. And I might be wrong about this one. I got to look it up. Sorry. So if you come over here and look up USD data types, we're talking about, so we did a 0.3f. So I did use the right one there, array. So I could have done that, but I do know I got the right one. The other one was int array. And so I could just do a regular list of integers. So that's fine. I like that. So we can come over here. So that's kind of nice because it's laid out. Every line is a face. And then this one we don't care too much about. In fact, we can just do four times 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 faces. All right, so that's just going to give us an array of 10 elements, all with the value of 4. So now create face vertex indices. And lastly, create face vertex counts attribute, and we give it the face vert count. We can make that plural. All right, if we run that now, has no attribute vec3f array. I should be able to create this. Maybe it's under VT. That's probably what it is. There it is. Okay, so regular data types are in Graphics Foundation. Arrays are in this VT module, which has all the array logic. So that worked out. Now we can look at our ARM again, and these look good. And theoretically, I'm going to open up a new instance of USD View, and we can keep an eye out on how this is coming together while also still having this one open for reference. So here we go. It's going to be in C extension. That means that I have this test arm here that I want to get rid of. That was my mistake earlier. And what did we call this? Omni code with me. Okay, so that's going to load, hopefully. Um, that all is fine. Yeah, I'm not 100% sure what happened here. We'll move this out. Just as a sanity check. I think I have everything that I need defined for a mesh for this to work. Low, smooth shaded. Just trying to make sure I didn't change any rendering settings here that might not get it to show. But this is why we check. Not backface culling. Definitely weird. One more thing we could do, just as another sanity check, is if I redo that. There we go. So that's good. So which part broke? I wonder if it's not liking the rig in there as defined right now. There it is. Okay, odd. So we'll leave out the rig for now until it's kind of all nested in there. So I'll have to keep just pushing forward and I'll hack it around just to verify. All right. We're learning. Hey, Data Juggler. Sorry for being late on the chat there. Okay, so we've got our basic setup of this mesh. Do we need anything else on the mesh? We do need to do these prim vars and the skinning method. But I think we can start building the skeleton. I'm just checking here because these prim vars look like they might be defined on the skeleton and then inherited down into these. We can actually look at the USDA here. So the skull root doesn't really have anything. We do need to do, looks like the skull binding API is applied onto the skull root. I do need to set the up axis. What's mine set to right now? It's the default, so we're good. Okay. Yeah, let's just move on to the skeleton because that's where all the interesting bits are going to be right now. And then we'll come back to the mesh. Okay, so for the skeleton, we need to define the joints. And then their binding transforms, their rest transforms are going to be identical to the binding trend. No. I guess, yeah, they defined that rest transform on the 2, which is odd, but we can change that. And then we'll do the animation last. Okay, got our game plan. So we've got our skeleton, and with the skeleton, anyways, I can take a little break here to talk about why this type hinting is working so well, and autocomplete is working so well. So if you haven't seen Types USD, highly recommend it. This is published by Luma. Oops, that's weird. Still not ranking very well, but I just had it in my search bar. This was released by Luma, and basically just pip install this, and it adds a stub, a Python stub file in it, and it'll make code completion for the Pixar package work in your code editor. So repository is here. This was, I think Chad did most of the work here. So thank you for that. I will put the link there for everybody. And cool. So we're going to add, well, let's do the joint adder first. And this one's a list, right? It looks like a list of tokens. Python the Python API is very happy with just strings for the tokens. So come over here, copy this exact list. And if we remember, the forward slashes are defining the hierarchy for these bones. So that's why we saw them parented to one another. Elbow is parented to shoulder, hand is parented to elbow, and we get that 3-joint chain. So we're just going to pass that list straight into there. And skeleton, create the bind transform. And we're also going to, we don't need it, the rest transform, but we can do it just to have what was there. So bind transform. This is a matrix 4D and it's an array of matrix 40. So what we need here, find xforms, bt, matrix 4D array. And then there's our array. And we have 3 of these. Okay. And then we just pass that right in. And then rest transforms. This is where I'm going to deviate a little bit because I feel like the rest transform is wrong. Basically what this rest transform is saying is, and this is the same, right? Rest transforms is also a matrix 40. What this rest transform is saying is that the default values for these joints, the default positions, it's saying that it wants the elbow on the hand on top of the elbow. And that just seems like an oversight there. So I think it's the rest transform, the logical rest transform would be the bind transform. It's just the 3 joints stretched out. Maybe you could do a slight relief on the elbow so that it's not super tight, but that's what we're going with. Blue squiggly is just thinks that's not a word. Of course, xforms is a word. All right. That's it for the skeleton. Okay, let's run it and make sure we got some. Whoops. No registered converter. Okay, this one's the one that's going to be interesting. So it doesn't want a tuple of tuples. Would it be happier with lists here? So this all comes down to like the convenience of Python to USD conversions. Sometimes it's nice. Sometimes it's a little hard to figure out what it really wants. So here I'm probably just not going to fight it and do a list of GF matrix 4s. So I see. I used to call it tuple as well until Papa Chuck corrected me, and he was right. I think both are fine, but I did look into it, and it sounds like tuple is correct. I don't remember why though. I did look this up at one point, and I was convinced that Papa Chuck was right. Oh, they're doubles. Okay. My bad. It wants double. Sorry. I don't know if I guess this is a situation where I think I have to do it this way. Because otherwise I wouldn't be able to decipher from, you know what, actually, if this was hard coded with float values, it probably would have accepted the first my first pass. But this is more robust for sure. Um, so there we go. Microsoft used tuple. I'm gonna trust Papa Chuck over Microsoft for sure. Um, no, like I said, it's probably fine. But I did look it up at one point, and I really didn't want to change, but after looking it up, I was convinced I needed to. Okay, we ran this, and here are our bind transforms, joints, and rest transforms. Beautiful. If anybody can look up the why it should be tuple and not tuple, feel free to share it in the chat and help educate us. And if you find a compelling explanation why it should be tuple, I will change back to my old ways. Okay, so we got the skeleton. We'll come back for the animation source bit. Joint names, if you remember, that's like pretty names that you can give to your joints. We don't need that. I do wonder if this will load now. Hey, yeah. Interesting. Oh, interesting. So that's 4 units out. Oh, I learned something. Bind transforms are in world space. Rest transforms are in local space. That's why it's a 2, because 2 plus 2 is 4. Okay, so these should not be identical. All right, who cares about my parents? Okay, so, and I think if we look at the documentation, if we read the manual, I do think I remember seeing that. World space, rest transforms, local space. Cool, cool. Okay, so if we rerun this, now it should be correct. And this is why we do the visual validations, people. There we go. That looks correct. Okay. And so we absolutely need that rest transforms, I think. I think that was still optional, and I think it would have been okay without it. But let's move on. Ba-ba-ba-bum. Okay, so we're done there. The original skeleton had the binding API. Are we ready for that? I think so. So I think these indices and weights are going to come from the binding API. So let's find out what that's all about. Just make sure there isn't anything else here that before I go looking elsewhere. Doesn't look like it. Looks like a fairly generic prim there. So USD scale binding API. Apply. I think it wants the prim here, not the schema object. And from what I saw, it's applied on both. We may need to read into why that makes sense. But it does look like there's the binding API on the model, which is the root. And then the mesh also has the binding API. That has the bind transform, and then the root doesn't really have any extra bits there. So we need to find out mesh. Do I need to apply we'll look into that. Okay. So we have our mesh. We've applied it. Let's just run that and see what that looks like in the USDA. So now we have both of those schemas applied. So that's good. That's step one. Does that, I think that returns an API object. Let's find out. It does return the binding API object. So this is a little awkward. I don't know. I don't know if I've ever done this, but I guess I have a binding API 1 and a binding API 2 because I'm applying it twice. Those are technically two different objects. So I would probably have to use one for one and one for the other. So we're going to ignore the scale root for now because we don't need to apply any properties, it looks like, for that one. So we'll just do it for this one. And we're going to need, we'll get to the animation. Let's take a look here. It's easier to look here because that way I know I'm only looking at the parts that are relevant. We need to apply the skeleton, joint indices, joint weights, and geom bind transform. And you can relist the joints here, I think, if I remember correctly, but so this must be pointing to, it wants a relationship. So we'll do scale root get prim, where it's going to create that relationship. And then binding API too. It's kind of a good idea to run these one by one so that I can see what that's doing in USDA. What does it want? Try that. It wants an SDF path, no problem. Okay, there we go. So what did we do here? On the mesh, we created this scale skeleton, and it's pointing to world arm. So we did that binding there. I am curious if when I do that, does it apply the schema onto that one? Probably not. Onto the scale root? No. Okay, so it does seem like we need to do that still manually. Okay, step 1, done. Joint indices, joint weights. Let's do indices. Okay, so now we're going to say, I think these are convenience functions. I want to say that they do the same thing, but we should look at the documentation for that one. This is the binding API. Um, this is by class, so USD scale. Binding API. And if we look, okay, so it is a convenience function to create joint indices prim bar. Optionally specify the element size. So we can try both just to see what that looks like. So default value here. This is what we're going to use. It's an int array. And if we'll look at this interpolation and element size in a moment. If we remember, our joint order is shoulder, elbow, hand. It's from the origin out. But our point order is hand, shoulder, elbow. So when we want to do this, we want to do this is gonna hand, shoulder, elbow. Now you see why I wanted to keep this in the order that I wanted. So first is shoulder, which would be, I guess it's doing it in reverse order. What is this doing? 0 is shoulder. No, 0 is hand. 1 is shoulder. So it's doing it in reverse order. It's doing... No, I don't know what it's doing. Blah, blah, blah. I thought I knew what was going on here. Let's see. So I did put this back into the order that it was in. And we can put comments here again. This is hand. Shoulder. Elbow. So it's doing elbow, hand, and shoulder. Let me double check here. Shoulder, elbow, hand. Read this again. This doesn't have a joints attribute defined. This one does, and it's in the order that I specified it in. So it did hand. Oh wait, that's right. Wait, hand. Right, okay, I think I was backwards. So this is saying for each of these vertices, which joint does it correspond to? Ugh, okay. So this is the order of the joints in the joints array. So for the first 4, we're talking about hand, which is correct. For the next 4, we're talking about shoulder, which is correct. That's at the 0th, or at the 0 position. And then for the last, we're talking about the elbow, which is at 2. And this is why I wanted to keep them in order. But I'm glad we made sense of it. Okay. My bad. This is indexed in joints property for each vertex. Yeah, so let's see what that does. Does it give us the full prim var? It does, see? But I can't specify the it'd be a little bit trickier to specify the element size if we look at mesh, join indices, metadata, I don't remember if I have an easy way to check the default values for this. I suppose, actually, we could look it up here. If we reopen this stage, we can see, I think we should see. No. So we'd have to look at the schema in order to find what those default values are. So if we looked at, I don't know why I thought that the default was -1 and something else. See, at least the default values for this function is constant in element size, which makes me think that that's the default for the schema. Pixar USD. So if we look at USD scale, it's not super important. I thought I could find this quickly, but we can just override it to be certain. Actually, hold on. There it is, schema USDA. So if we look at the schema USDA in USD scale, we should find in there binding API, right? We'll get over that hump there. And scale binding API. And then if we look at join indices, there must be an easier way to look this up. It doesn't define the default value. Define a default value. Well, all right then. I thought if there is a default value, I think we should see it here. And an easy way to check that, or an easy one to compare on that I know should have it, is USD geom schema. If we look for sphere, it has a radius and it also defines a default value. Whereas with the other one, we didn't see that, right? Come on. Man, it's already 11. It's been an hour. Scale binding API. Joins, yeah. Okay, so it doesn't look like it has a default value. So let's go ahead and use the primvars API, and we're going to give it vertex and element size of 1, I think is what we had. And we'll stop there, I think. So we're going to, instead of indices adder, we're going to do primvar, and that's going to want the data. No, I guess it wants, the API is a little bit different here. It wants constant is false. Element size is 1. Okay. And so now I should be able to do join indices. This is a primvar object, so then I can do set that. And if we come over here, we now see our joint indices with the element size and the vertex like we want. Cool. I think we can stop there for now. I don't know what changes the comments. We can leave the comments. Let's do joint weights just to round it out here. And same deal, vertex and element of size of 1. And I think we talked about this last time. It's the primvar rate is vertex because we want to be able to, for every vertex in the mesh, we want to be able to specify which joint is influencing it, and also by how much is what the weight is in this case. And then element size, if you remember, is you specify that if there's going to be multiple joint influences on a single vertex, you use element size for encoding that. And then we can grab it from here. They're all 1s. It's not a bad idea to leave those spaces there. Okay, so ours should look like that now too. Sweet. Okay, I think we'll wrap this up next week. What do we have left to do? We have to do the bind transform and add the scale animation and set the animation source for the skeleton. Okay. I think we can call it here. I think that's going to take us at least another 15, 30 minutes. So I don't want to go too long. Thank you for joining, everyone. If you have any questions, please feel free to reach out. And once we build out this script for building a basic armature, binding it and animating it, I think we can then explore some more advanced concepts like the blend shapes, or I don't know what else that character had. Blend shapes are definitely on my mind. So I thought it'd be cool to do an example where again, just a cube or a rectangular prism example, but we can do some simple blend shapes, so we'll get the full effect, but it'll be easy to digest what's going on there. So we can use blend shapes just to scale one end of the mesh, for example, and animate that. Um, I don't know why I'm looking in there. Scale root, skeleton, and this one doesn't have any animation, but blend shapes are definitely a big part there. And then the other question that I have is, if we looked at the animation one, the joint lengths were different. Also, it might be interesting to do rig complexity and geometric, take a deeper look into what this is doing with the geometric LODs and the rig complexity. That might be interesting to study. All right. I hope you have a great week. I will be back for Friday for Developer Office Hour. So if you have any questions, bring them there. And I'll see you later.